let's take a look at the farthest in future algorithm. We're going to prove this using induction, and the proof works something like this. So assume that there's an optimal algorithm, which there is. And here's our algorithm, farthest in future. Farthest in future. And right here is going to be our cache, so that we can keep track of whose caches contain what elements. So let's say at some point the optimal algorithm and our algorithm are going to differ. Now, we know that they start off the same, so that's our base case. Then assume that they stay the same for j elements. We need to prove that we can do it for j plus 1. So instead of proving that our algorithm and the optimal work up to j plus 1, we are going to construct a separate algorithm, O prime, and show that it and our algorithm match up to j plus 1. So we said that at the jth element, our algorithm and the optimal differed. So let's say that we both had h, but then when it came to the jth step, the optimal threw out element f, and we threw out element e. So we have f and they have e, and we both took in h, let's say. So we differ with one element now, which makes sense because this is where we differ. Now we just need to show that O, which has hf, which means that it matches us for the j plus 1 element, we have to show that this algorithm is still optimal. So an important thing to keep in mind right now is that O prime and our algorithm match for the j plus 1 element, but O prime is not restricted to the farthest in future restriction. So whatever it does, how it drops and how it picks up elements, that has nothing to do with the farthest in future. So because of that, we should be able to get O prime back on track with O and keep it optimal. So how are we going to do that? So we have a few cases. So let's say that the incoming element, is G. We'll say it's G. We have case 1. Case 1 is that G is equal to H. Okay, with this case, O and A are the same. We don't even have to look at O prime in this case, because in both cases, in this case, when G is equal to H, both the optimal and our algorithm don't take in H because we already have it. So that means that they both succeed up to the j plus 1 element, and they match each other. So they're both as optimal. So we've proven it for j plus 1 in this case already. The interesting case is case 2, and that is when G is equal to F. Here we have the element, or really I should say O prime has the element, F, but O doesn't. So there are two options. A, O drops H for F. In this case, O, what does its cache look like? It looks like F, E. So somehow, we have to drop in O prime to get FE. And if that happens, we'll have the same cache as O, the same number of cache misses because we both dropped on the J plus 1th, and then we'll just have O prime continue doing whatever O does, and it will remain optimal. So what we're really trying to do is we're trying to get O to match we're trying to get O prime to match O's cache. So how will we do this? Well, then in this case, O prime drops H for E. O prime will drop H, pick up E, then it will have FE, O has FE, and we have the same number of cache misses, and therefore O prime is optimal. And we've just proven that there's another optimal schedule that matches our schedule for J plus 1. Okay. What's B? Option B is O drops E for F. In this case, O is going to have what? O is going to have HF. That's the same as what we already have, HF. So we don't have to do anything. So we are already optimal, right? We have the same exact cache as them with one less cache miss, and from this point on, we just copy whatever O does and will remain optimal. So O prime is optimal in that case. So that is the two options, A and B, for case 2. There's only one other possibility. That's case 3. And that is that G is equal to E, which means that O has it and we don't. And that's a problem, because in that case, we have to drop and they don't. And if we have to drop and they don't, that means that we're going to have one more cache miss than they have. So how do we deal with this case? Well, this case actually can never happen. It's impossible. So why is that? Here's where we use our algorithm's main property of the fact that it's farthest in future. Our algorithm guarantees that case 2 must happen before case 3. Why? Because we, in our farthest in future algorithm, dropped E and O dropped F. But if we dropped E, that means that E will occur farther in the future than F will occur. That's the whole idea of our algorithm, which means that there has to be an F somewhere before E. And if that's the case, then case 2 will occur. Whenever that F shows up, G will equal to F. And whenever that happens, we will be equal to O again. So we've just proven that the only two possible cases are case 1 or case 2, and in both of those cases, we can get back in line with O while not getting any more cache misses. Right? Either we don't take anything in, and they don't take anything in, and we're the same, or they have to take in, and we don't, or they have to take in, and we have to take in, but regardless, we can match their cache within one step without gaining more cache misses than them. And once we match their cache, we just continue doing whatever O does from that point on. So the last part of this algorithm is just showing the induction part, and that is that if once we show that A and O prime can match up to the J plus 1 step, and that O prime is optimal, you can just move O prime up to the top here, and then continue this process. So the next time that O prime and A differ, we should be able to come up with an O prime prime that matches A for one more step than O prime and is still optimal using the same proof. And that can repeat itself on and on and on until all of the elements match A, and then we have an optimal algorithm that matches A. So hopefully that explains the proof.